Okay, I have a challenge for you. Here is a beam in bending, and we want to find the maximum stress. So pause the video and see if you can do it. Okay, I'm assuming you did that. So now let's do it together. So where would we start? Well, we would start by finding global equilibrium. So let me write here, global equilibrium. And we're gonna start by finding our reaction forces. So if we do the sum of the moments about point A, where the moments are positive going this way, we know they have to be equal to 0 because it's not moving. And so we're gonna have what, minus 150 times its area, which is 4 and 4 and 4, which is 12. At what location? In the middle, so that's times 6. And then we'd have minus 750 pounds multiplied by the distance from A, which is 4, and minus 750 pounds. I think it's going to be symmetric. Yeah, I think it's going to be symmetric, and you'll see. 758 times 8 plus by times 12. All of that must be equal to 0. So let me do that real quick. 150 times 12 times 6 plus 750 times 4 plus 750 times 8. All of that divided by 12. You get 1650. So By is equal to 1650 pounds. And now if we do the sum of the forces in the y direction where up is positive, we get AY plus 1650 minus 2 times 750, which is 1500, and then minus 150 times 12. What we get is, let me see, 1650 plus 1500 plus 150 times 12, we get 1650. So as I said, it's going to be symmetric. So we could have done that by inspection. And now we can draw the free body diagram. So right here, this, and right here, this, and then what? And then I'm going to make a cut here. Oop, that's not what I wanted to do. I'm gonna make a cut here, and I'm going to make another cut. I don't know why sometimes my iPad does this thing where it just goes all the way to the top whenever I try to draw a line, and it might do it again. See? Yeah, it did again. Okay, so now we're gonna decide our cuts here, here, here. We're now going to draw our beam, our cut beams. So right here is the first one. Then we're gonna have another one right here. And then finally, we're gonna have one last one right here. And so here we're gonna have the shear V1, M1, V2, M2, V3, M3. We're going to have the reaction force, which is 1650. So right here is 1650 for all. 1, 650. 1, 650. 1, 650. And then here we're gonna have distributed a load, which is at a height of what? Is at a height of 150. So this one as well. It's at a height of 150. I'm gonna draw fewer arrows just because I'm lazy. All right. And then right here. Okay. Let me draw one more. Okay, 150. But then we also have other things. Here we have a 750. I'll change color just to make it clearer. Here we have a 750. And here we have a 750. All right? So remember what we're after. We're after the stress. Or if we can pick the highest moment, so we don't really need the shear, but it's nice to have it just for review. Then we can use that in the flexure formula, assuming that this is pure bending, which is not, but we can assume that it still works for certain conditions, which are kind of, we're still in the elastic region, this beam is slender, and the moments are symmetric about the y-axis, and the beam is straight prismatic and a homogeneous beam. Okay, so for the first part, we're going to go from 0 to 4, and we're going to say V1 is equal to minus 150 times x, and M1 is minus 75x squared. Do you see why? So we can evaluate them. V at A is equal to 0. Well, we forgot to put the 1650. So V at A is equal to 1650. And V at C from the left is equal to 1650 minus 1650 minus 150 times 4, which is 1050. Okay, and these are in pounds. So this is pounds and this is pounds. Now, M at A should be 0. It is. M at B is going to be equal to minus 75 times 4 squared, which is 16. And what do we get? What do we get? Well, minus 12. 0 pounds feet. Okay. Then we're going to look at the second part. So let me make a little bit of a separation here. Second part, my x is going to be between 4 and 8. And my V1 is going to be what I had before, minus 150 times x, because this is again x, minus 750 plus 1650, which becomes what? Becomes minus 150x. And now 1650 minus 750 should be 900. Okay, plus 900. And now we can do M, and this is B sub 2. Sub 2, M sub 2. That's going to be what we had before, which is minus 75x squared. And then minus, because it's making me frown, minus 750 times x minus 4. Right there. So what can we say now? Well, we can simplify this a little bit by distributing 750x plus 750 times 4. I'm going to try and do it in my head. It's 2,800 and another 200, so that's 3,000. Yes, 3,000. Okay, so now we can say V at C from the right is going to be minus 150 times 4 plus 900, which is 300, which does it agree with the fact that we're going down another 7,500? Yeah. So 300 pounds. And then VD from the left, well, now it's going to be minus 150 times 8 plus 900. So that's going to be minus 300 pounds. Okay. And now we're going to do MC. Should be the same. Oh, and this is a C. Should be the same as that. And so, let's see, minus 75 times 4 squared minus 750 times 4 plus 3,000. We get minus 1,200 pounds feet. M at D is the same thing, but now instead of putting the 4 squared, we put what? We put the 8 squared, which is minus 4,800 pound feet. Okay, so these are some other points. We got one last cut to go. All right, let's not get discouraged because we're getting there. We're getting there. I see the light. So now my X goes between 8 and the end, which is 12. So it goes between 8 and 12. And what are we going to put in? Well, let me see right here. So V3 is going to be what we have before, which is minus 150x plus 900 minus another 750 plus 900 minus 750. So that really becomes plus 150. Minus 150x plus 150. Now, let's do the same with the M3. It's going to be the same as before, minus 75x squared minus 750x plus 3,000. And then we have that minus 750 times x minus 8. Minus 750 times x minus 8. So let's simplify that a little bit. Minus 75x squared minus 750x plus 3,000 minus 750x plus 750 times 8. 750 times 8, which is 6,000. And so what is that going to be? Minus 75 x squared minus 1500x plus 9,000. Okay, and now we want to say M sub D. Well, let's do the V first. V sub D from the right. Is that going to be V sub D from the right? That's going to be minus 150 times 8 plus 150, which is minus 1050 pounds. Does that make sense? Yes. And then VB from the left, we're going to do minus 150 times 8 plus, not times 8, times 12. Times 12 plus 150 minus 1650, which makes sense because then the reaction force brings it back to 0. And then M at D should be the same as before. We'll see. Minus 75 times 8 squared minus 1,500 times 8 plus 9,000 is minus 7,800, which tells us that we did something wrong with the math again. Because it should be minus 4,800. So let's see what we did wrong here. So for M3, we're gonna have a 75 times x squared. Why? Because it's gonna be 150 times my total length, which is right here, and it is x, times my total length at a distance of x over 2 from the cut. So that's going to be 75x squared. And it's making me frown, so it's negative. Then I'm going to have a 750 times the distance, x minus 4. So that's the same thing as the minus 750x. And 750 times 4 is going to be 3,000. And it becomes positive. And then I have another force, 750. And 750 times 8, which is 6,000 positive. So 6,000 plus 3,000 is 9,000. And then we have 750 and 750, which becomes 1,500x. So overall, it looks like that's correct. But, and let's see, when I get minus 75 times 12 squared minus 1,500 times 12 plus 9,000, I don't even get 0. So let me see in my other times I've done this problem where the mistake might be. I have to find it. Okay, I found it. It looks like the first expression for V1 is 1650 minus 150x, and that's what I had. And then here, that's where we made the mistake. At the very first, because we have the 160 plus the 1650 times x. And so that's going to change all of our results. So minus 75 times x, which is what? X is 4 squared plus 1650 times 4. We get 5,400 here. So here we get 5,400. And so that's going to change here as well, because we're also going to have a plus 1650x. So 1650 minus 750 is going to be 900 over here, positive 900. And so that would mean that here we get 5,400. And then here, we're going to get minus 75 times x, which is 8 squared, plus 900 times 8, plus 3,000. We get 5,400. And then, once we get to here, that was incorrect. Let me fix it. So that's positive 900. And then that part is correct. So you just forgot to put the reaction force. So forgot to put the reaction force, and then in the previous exercise, when there's a concentrated load, and you're looking at this, for example, here's my cut. Does this make me frown? Well, you'd see this and you would think, well, if it was here, it would make me frown. But actually, it's not there. And so it's really a force pushing this way, an equivalent force pushing down that way. So it looks like it's making me smile from the cut, right? So be careful with that. And if you get confused, I would just do the global equilibrium for that one. And that's referring to the previous problem I just did. Okay, so that's a little self-reflection on the mistakes. And that's, now we can keep going here. Minus 750x plus 750 times 8 is 6,000. And so if we add all these things up, we get minus 75x squared plus, so minus 75x plus 18,000. No, I don't know where I got that because I wasn't looking at the 900. Okay, so plus 150 plus 150x plus 9,000. And so if you do that, what do you get? Minus 75 times 8 squared plus 150 times 8 plus 9,000, 5,400 pounds feet. And then MB is going to be 0 if we did it correctly. So let's see, minus 75 times 12 squared plus 150 times 12 plus 9,000, we get 0. Okay, so now we can go ahead and do our shear and bending moment diagram, because remember, we're after the max moment. And don't give up, we're almost done. Okay, so we're extending these, and then what else? Hold on, I need more. All right, so, oh, that's too much. Okay, so now, what I'm gonna do is I'm going to draw the shear and bending moments. So V is gonna be in pounds. The moment is gonna be in pounds feet. And let's see, we start from positive 1650 right here, and we go down to 1050, 1650, 1050, and then we go to 300, and then we go to negative 300. So 300 negative, don't put the negatives, they don't like that. And then shear goes down to 1050, and then goes here. Nope, it's not gonna be straight. So 1050 is much closer. I drew it much closer to the X, so kind of like this, 1050, and then it goes down to 1650, and then it goes to 0 right there. The slopes should, I'm trying to think if they should all be the same. Well, minus 150 in all of them, yeah. They should all be parallel. Okay, so that now we're gonna look at the moments. The moment is quadratic, negative, so it's concave down. Go from 0 to 540, and then from 540 to 540 again. So we're going to do this, this, and this, essentially. And so our max is right here. We don't know. This is 540, and this is 540, and this is 0. And that is 0. So to find our max, what we do is we look at the second cut, finding M max. We look at V2 and we say that we want the x when that is 0. So that's going to be x is equal to 900 minus 150. It's the same thing as 90 divided by 15, which 15 will fit 6 times. So at 6 feet, we're going to have my M max. Now we have a function for that. So let's put everything into the function. And so what is our function for M2? Minus 75x squared, so minus 75 times 36. We'll drop the units. Minus 75 times 36 plus 900 times 6 plus 3,000. What is that? Minus 75 times 36 plus 900 times 6 plus 3,000. That's going to be 5,700 pounds-feet. We'll write that over here. 5,700. We don't need the units here. Okay, so now what? Well, now what we can do is we can find the max stress. So S max is going to be minus mzy max iz, which is equal to what? Well, we found 5,700, and this is in pound feet. So we got to convert it to inches, right? Because the cross section is in inches, times 12 inches in a foot, times the distance to the max is halfway of 12, which is 6 inches. So times 6 inches divided by 1 over 12. The base is 3, the height is 12. 312 to the third. So what is that going to be? Minus 5,700 times 12 times 6. All of it divided by 3 times 12 squared. Minus 950 pounds over inches squared, which is PSI. Woo, we got this. I hope this was useful for you, and I will see you next time. So again, what was the mistake I made is I forgot to put the reaction force 1,650 at A. So don't do that.